Right now, humanity has achieved something that would have seemed impossible to our ancestors just a few generations ago. We have built machines that are racing through the cosmos at speeds so incredible they make a bullet look like it's standing still. So just how fast can we actually travel in space right now? And what does that mean for our cosmic future? But one quick question: if you could break one law of physics for a day, which one would it be? And what would you do? Let me know in the comment down below. I will pin the most creative answer. Now let's begin. To understand how fast we can travel in space, we need to start with the fastest human-made object ever built. Right now, racing toward the Sun at an absolutely mind-bending speed is NASA's Parker Solar Probe. This incredible spacecraft, launched in 2018, is currently moving at about 430,000 miles per hour. That's roughly 120 miles per second. To put that in perspective, this probe could travel from New York to Los Angeles in about 20 seconds. But even that incredible speed tells only part of the story. You see, the Parker Solar Probe is using something called a gravity assist, essentially stealing energy from Venus's orbital motion to slingshot itself faster and faster toward our star. With each close approach to Venus, it picks up more speed. By 2025, when it makes its closest approach to the Sun, it will reach speeds of over 430,000 miles per hour, making it the fastest human-made object in history. This isn't just about breaking records, though. The Parker Solar Probe is rewriting our understanding of how the Sun works, diving into the solar corona, where temperatures reach millions of degrees. It's sending back data that's helping us understand space weather, solar wind, and the fundamental processes that power our star. This tiny spacecraft, weighing less than a small car, is essentially touching the Sun for the very first time in human history. But let's zoom out for a moment and consider what this speed really means in cosmic terms. At 430,000 miles per hour, the Parker Solar Probe could reach the Moon in about 9 hours. It could get to Mars, when the planets are closest, in about 2 to 3 months. That sounds pretty impressive until you realize that even at this incredible speed, it would take over 9,000 years to reach Proxima Centauri, our nearest stellar neighbor. 9,000 years. That's longer than all of recorded human civilization. The ancient Egyptians were building the first pyramids about 4,500 years ago. At our current maximum speed, we're looking at twice that length of time just to reach the closest star beyond our Sun. Now you might be wondering, why can't we just build faster rockets? The answer lies in something called the rocket equation, and it reveals one of the most fundamental limitations we face in space travel. Every rocket works by throwing mass in one direction to push the spacecraft in the opposite direction. But here's the cruel catch: the fuel itself has mass, and you need fuel to accelerate that fuel, which means you need more fuel, which has more mass, creating what engineers call the tyranny of the rocket equation. Chemical rockets, like the ones that took us to the Moon and launch our satellites today, can only achieve what's called a specific impulse of about 450 seconds. That's a measure of how efficiently they use their propellant. No matter how you design a chemical rocket, you're limited by the energy stored in chemical bonds between atoms. It's like trying to power a car with muscle power instead of gasoline. There's only so much energy available in the system. But we've developed more advanced propulsion systems that can achieve much higher speeds over time. Ion drives, used by missions like NASA's Dawn spacecraft that explored the asteroids Vesta and Ceres, work by electrically accelerating ions to incredibly high speeds. These engines produce thrust that's barely more than the weight of a piece of paper, but they can operate continuously for years. The Dawn mission, launched in 2007, used ion propulsion to become the first spacecraft ever to orbit 2 different celestial bodies in the same mission. It spent time studying Vesta in 2011 and 2012, then fired up its ion engines and spiraled its way to Ceres, arriving in 2015. This wouldn't have been possible with chemical rockets. There simply wouldn't have been enough fuel. Hey, if you're enjoying this cosmic journey through our current capabilities in space, hit that subscribe button and give this video a thumbs up. Trust me, we're just getting started on this exploration of how humanity is pushing the boundaries of speed and distance in the vast ocean of space. Ion drives can achieve much higher specific impulses than chemical rockets, up to 3,000 seconds or more, but they face their own limitations. They require electrical power, usually from solar panels, or radioisotope thermoelectric generators, which limits how far from the sun they can operate effectively. And while they're incredibly efficient, they accelerate very slowly, taking months or years to build up to high speeds. Then there are solar sails, which use the pressure of light itself for propulsion. Japan's Icaros mission, launched in 2010, proved that solar sailing works in practice. These spacecraft deploy enormous, ultra-thin reflective sails that catch photons from the sun or powerful lasers. The thrust is incredibly gentle, less than the weight of a paperclip, but it never stops as long as there's light. The beauty of solar sails is that they don't need to carry any fuel at all. They're essentially surfing on Starlight. The Planetary Society's Light Sail 2 mission, launched in 2019, demonstrated controlled solar sailing in Earth orbit, using only the pressure of sunlight to change its orbit. It's a technology that could potentially accelerate small spacecraft to incredible speeds over time. But here's where things get really interesting from a cosmic perspective. The speed of light, 670 million miles per hour, represents the ultimate speed limit in our universe. Nothing with mass can ever reach that speed, no matter how much energy you apply. As you approach light speed, your mass effectively becomes infinite, requiring infinite energy to accelerate further. It's not just an engineering challenge, it's a fundamental law of physics that governs how reality works. This speed limit isn't arbitrary, it's woven into the very fabric of space and time. Einstein showed us that space and time are connected, forming what we call space-time. The speed of light is actually the speed at which cause and effect can propagate through space-time. It's the speed at which information itself can travel. When you look up at the night sky, you're seeing the universe as it was in the past, because light takes time to reach your eyes. This cosmic speed limit creates a profound sense of scale that's almost impossible to comprehend. Light from our nearest star, Proxima Centauri, takes 4.2 years to reach Earth. That means when you look at that star through a telescope, you're seeing it as it was over 4 years ago. The light hitting your eyes began its journey before the COVID pandemic, before many of the events that have shaped our recent world. Now imagine if we could somehow break the laws of physics and travel at impossible speeds. I actually made an entire video exploring what you'd see if we could travel at 1 light-year per second across the cosmos. The sights would be absolutely mind-blowing. From racing past entire star systems in heartbeats to watching the structure of galaxy clusters unfold before your eyes. The link is in the description and on the card above. So what are the practical limits for spacecraft we can actually build? The fastest speeds we've achieved with chemical propulsion came during the Apollo missions. When Apollo 10 returned from the Moon in May 1969, it reached a speed of about 25,000 miles per hour relative to Earth during re-entry. That's still the speed record for a crewed spacecraft returning to Earth's atmosphere. But we've achieved much higher speeds with uncrewed spacecraft using gravity assists. The Helios probes, launched in the 1970s to study the Sun, used gravity assists from Jupiter to reach speeds of about 157,000 miles per hour. The Voyager probes, launched in 1977, have used multiple planetary gravity assists to achieve their current interstellar velocities of about 38,000 miles per hour. Voyager 1, now more than 14 billion miles from Earth, is humanity's most distant ambassador to the cosmos. It's currently traveling through true interstellar space, the region between stars, sending back data about conditions in this alien environment. But even at its impressive speed, Voyager 1 would take about 73,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. These gravity assists, also called gravitational slingshots, are like cosmic theft. We're essentially stealing orbital energy from planets to accelerate our spacecraft. When a spacecraft approaches a planet from behind in its orbit, it gets pulled along by the planet's gravity, gaining speed. When it leaves, it's moving faster than when it arrived. The planet loses a tiny amount of orbital energy, but since planets are so massive compared to spacecraft, the effect is negligible. The math behind gravity assists is beautiful and was first worked out in detail by Michael Minovich at NASA's Jet Propulsion Laboratory in the 1960s. He realized that by carefully timing spacecraft trajectories, you could use the gravitational fields of planets like a cosmic pinball machine, bouncing from one world to another and picking up speed with each encounter. This technique made the Grand Tour missions like Voyager possible, allowing us to visit multiple outer planets in a single mission. But even with perfect gravity assists from every planet in the solar system, there are limits to how fast chemical propulsion can take us. The exhaust velocity of the best chemical rockets tops out at around 3 miles per second. That's the fundamental limit imposed by the energy stored in chemical bonds. To go faster, you need more energetic propulsion systems. Nuclear thermal rockets could potentially double or triple our exhaust velocities. These systems use a nuclear reactor to heat propellant to much higher temperatures than chemical combustion can achieve. NASA tested nuclear thermal rockets in the 1960s and 70s under Project Nerva, achieving impressive performance. The technology works, but it comes with obvious challenges related to launching nuclear reactors into space and the political complexities that involves. Even more exotic are nuclear pulse propulsion concepts like Project Orion, studied in the 1950s and 60s. The idea was to accelerate a spacecraft using a series of small nuclear explosions behind a massive pusher plate. The calculations showed that such a system could potentially reach 5% of light speed, enough to get to Alpha Centauri in about 80 years. But the engineering challenges are staggering, and the political implications of detonating thousands of nuclear devices in space make it unlikely we'll ever build such a system. Fusion rockets represent the holy grail of near-term propulsion technology. Fusion reactions release about 10 times more energy per unit mass than the best chemical reactions. If we could build reliable fusion rockets, we could potentially reach Mars in weeks instead of months, and the outer planets in years instead of decades. But despite billions of dollars of investment and decades of research, we still haven't achieved sustained fusion reactions that produce more energy than they consume. The ITER project in France represents humanity's best current attempt to demonstrate controlled fusion. This massive international collaboration has been under construction for decades and might achieve its first plasma in the late 2020s or early 2030s. But ITER is designed to prove fusion is possible, not to be a practical power plant. Converting fusion technology into rocket engines would require additional breakthroughs in materials science, magnetic confinement, and propellant handling. Antimatter propulsion represents the theoretical upper limit of rocket efficiency. When matter and antimatter annihilate, they convert their entire mass into energy according to Einstein's famous equation E equals mc squared. This is the most energetic reaction possible in the universe, releasing about 3 orders of magnitude more energy than fusion. In theory, antimatter rockets could achieve significant fractions of light speed. The problem is that we can barely make antimatter at all, let alone store it safely. The Large Hadron Collider at CERN produces about 10 billion antiprotons per minute, which sounds impressive until you realize that's only about 1.5 femtograms, a billionth of a gram. At current production rates, it would take billions of years to produce enough antimatter for a single interstellar mission. And storing antimatter requires perfect magnetic confinement. If even a few atoms touch the walls of their container, they annihilate and release their energy explosively. But let's step back from these exotic technologies and consider what we can actually achieve right now with existing propulsion systems. NASA's New Horizons mission, launched in 2006 to explore Pluto, achieved an initial velocity of about 25,000 miles per hour using a chemical rocket and a Jupiter gravity assist. It reached Pluto in just 9 years, incredibly fast for such a distant target. The European Space Agency's Solar Orbiter, launched in 2020, will use multiple gravity assists from Venus and Earth to achieve a highly elliptical orbit around the Sun. At its closest approach, it will be traveling at nearly 150,000 miles per hour relative to the Sun. This speed is necessary to match the orbital motion of solar material in the Sun's outer atmosphere, allowing detailed study of solar wind formation. China's Tianwen-1 mission to Mars, launched in 2020, used a direct transfer trajectory that took about 7 months to reach the red planet. This represents typical performance for current Mars missions, about 6 to 9 months, depending on the exact trajectory and launch window. While that might seem slow, it's actually quite impressive, given that Mars can be over 200 million miles away when the planets are on opposite sides of the Sun. These missions represent the current state-of-the-art in practical space travel. They use well-understood physics, proven technologies, and flight-tested systems. But they also reveal the fundamental constraints we face when trying to travel through space quickly and efficiently. Every mission is a careful balance between speed, fuel requirements, launch capabilities, and mission objectives. This brings us to one of the most important realizations about space travel. Speed isn't everything. Sometimes the most efficient path isn't the fastest one. Mission planners often choose longer, slower trajectories that use less energy and provide more reliable arrivals than high-speed direct routes. The trade-offs between speed, energy, reliability, and scientific return create a complex optimization problem that's different for every mission. Consider the Cassini mission to Saturn, launched in 1997 and arriving in 2004 after a 7-year journey. Instead of taking a direct route, Cassini performed gravity assists at Venus twice and Earth once before heading to Jupiter for a final speed boost towards Saturn. This complex trajectory, called a Voyager for Venus, Earth, Jupiter gravity assist, allowed the spacecraft to arrive at Saturn with much more fuel remaining than a direct trajectory would have provided. That extra fuel enabled Cassini to operate in Saturn's system for 13 years, making discoveries about the planet's rings, moons, and magnetosphere that wouldn't have been possible with a faster but fuel-hungry direct approach. The mission discovered liquid water oceans beneath the ice of Enceladus, observed methane lakes on Titan, and revealed the intricate structure of Saturn's rings in unprecedented detail. Sometimes, taking the slow road yields the richest rewards. The gravity assist technique represents one of humanity's cleverest solutions to the challenge of high-speed space travel. By carefully choreographing encounters with planets, we can achieve velocities that would require enormous amounts of fuel using rocket power alone. The Voyager missions remain the masters of this technique, using a rare alignment of the outer planets that occurs only once every 176 years to visit Jupiter, Saturn, Uranus, and Neptune in a single mission. That planetary alignment, known as the Grand Tour opportunity, was recognized by NASA mission planners in the late 1960s. The geometry worked so perfectly that spacecraft launched in the late 1970s could visit all 4 outer planets using gravity assists, something that would normally require separate missions to each target. Voyager 2 took advantage of this alignment to become the only spacecraft ever to visit Uranus and Neptune. But gravity assists have their limitations. You can only go where the planets take you, and you're constrained by orbital mechanics and launch windows. Sometimes, the most efficient gravity assist trajectory takes you far out of the plane of the solar system or requires waiting years for the right planetary configuration. Mission planners must balance these constraints against scientific objectives and budget limitations. The upcoming Europa Clipper mission, scheduled for launch in 2024, will use a complex trajectory involving gravity assists from Mars and Earth to reach Jupiter's icy moon, Europa. The spacecraft will take about 5.5 years to make the journey, but it will arrive with enough fuel to perform dozens of close flybys of Europa, searching for signs of habitability in the ocean beneath its frozen surface. Ion propulsion offers a different approach to achieving high speeds in space. Unlike chemical rockets that provide brief bursts of high thrust, ion engines can operate continuously for years, gradually accelerating spacecraft to impressive velocities. The Dawn mission demonstrated this beautifully, slowly spiraling its way from asteroid Vesta to dwarf planet Ceres, using gentle but persistent ion thrust. The physics of ion propulsion is elegantly simple. Electric fields accelerate ions to speeds of about 30 kilometers per second, 10 times faster than chemical rocket exhaust. While the thrust is tiny, less than the weight of a sheet of paper, it adds up over time. Dawn's ion engines operated for over 11 years, consuming only about 870 pounds of xenon propellant to achieve velocity changes that would have required thousands of pounds of chemical propellant. NASA's upcoming Psyche mission, launching in 2023 to visit a metal-rich asteroid, will use advanced ion propulsion to reach its target in the asteroid belt. The spacecraft will accelerate continuously for years, eventually reaching speeds that would be impossible with chemical propulsion alone. By the time it arrives at asteroid Psyche in 2029, it will be traveling at about 24 kilometers per second relative to Earth. But even ion propulsion has fundamental limits. The engines require electrical power, typically from solar panels or radioisotope thermoelectric generators. Solar panels become less effective as you move away from the Sun. At Jupiter's distance, they receive only 4% as much sunlight as they do near Earth. Beyond Saturn, solar power becomes impractical for high-power applications like ion propulsion. This is why missions to the outer solar system often rely on radioisotope power sources. The Cassini mission carried 3 radioisotope thermoelectric generators that produced about 885 watts of electrical power at launch. That's less power than a typical microwave oven, but it was enough to operate the spacecraft's instruments and communication systems for over 20 years. The Parker Solar Probe faces the opposite challenge: too much solar energy. At its closest approach to the Sun, the spacecraft will experience solar flux about 500 times more intense than Earth receives. Its revolutionary heat shield, made of carbon composite materials, must protect the instruments while allowing the spacecraft to actually fly through the Sun's outer atmosphere at incredible speeds. This heat shield technology represents a breakthrough in materials science. The thermal protection system uses a carbon-carbon composite that can withstand temperatures over 2,900 degrees Fahrenheit while remaining lightweight enough for high-speed maneuvering. The technology developed for Parker Solar Probe could eventually enable faster missions throughout the solar system by allowing spacecraft to fly closer to the Sun for more effective gravity assists. Solar sail propulsion offers yet another approach to high-speed space travel, though with very different characteristics. Instead of carrying propellant, solar sails use the momentum of photons, particles of light, for thrust. The Japanese Icaros mission proved that solar sailing works in practice, and subsequent missions like LightSail 2 have demonstrated controlled flight using only sunlight for propulsion. The beauty of solar sails lies in their theoretical, unlimited acceleration time. As long as there's light hitting the sail, there's thrust accelerating the spacecraft. Over months or years, even tiny accelerations can build up to impressive speeds. Computer models suggest that optimized solar sails could potentially reach several % of light speed, fast enough to make interstellar missions barely feasible within human timescales. The breakthrough Starshot project represents the most ambitious application of solar sail technology currently under consideration. The concept involves using powerful ground-based lasers to accelerate tiny spacecraft to 20% of light speed, fast enough to reach Proxima Centauri in about 20 years. While the technical challenges are staggering, the project demonstrates how advanced propulsion concepts might eventually enable true interstellar exploration. But all of these propulsion technologies share a common limitation. They're still bound by the fundamental physics of accelerating mass through space. Every spacecraft, no matter how advanced its propulsion system, must carry its own reaction mass or energy source. This creates the tyrannical rocket equation that limits how fast we can practically travel through space. The rocket equation, first formulated by Konstantin Tsiolkovsky in 1903, shows that the velocity change achievable by a rocket is proportional to the logarithm of its mass ratio, the ratio of initial mass to final mass. This logarithmic relationship means that achieving high speeds requires exponentially more propellant mass. To double your velocity, you need much more than twice as much fuel. This mathematical reality explains why spacecraft designers obsess over mass budgets and why every gram matters in space mission design. The Curiosity rover, which landed on Mars in 2012, had a mass budget so tight that engineers had to remove scientific instruments to make room for landing system components. Every design decision in space missions involves trade-offs between capability, mass, and mission requirements. Understanding the rocket equation helps explain why some of the most successful space missions have used seemingly counterintuitive approaches. The Ulysses mission, launched in 1990 to study the Sun's polar regions, couldn't fly directly to solar polar orbit because that would have required more energy than any rocket could provide. Instead, it flew out to Jupiter, used the giant planet's gravity to completely change its orbital plane, and then fell back toward the Sun in a polar orbit. This Jupiter gravity assist maneuver achieved something that would have been impossible with direct propulsion. To change a spacecraft's orbital inclination by 90 degrees in the inner solar system requires enormous amounts of energy, far more than any practical rocket could provide. But Jupiter's immense gravitational field made it possible to redirect Ulysses for essentially no fuel cost. It's a perfect example of using orbital mechanics and patience instead of brute force to achieve seemingly impossible goals. The New Horizons mission used a different but equally clever approach. Instead of trying to slow down and orbit Pluto, which would have required a spacecraft many times larger and more complex, mission planners opted for a high-speed flyby that collected maximum science data in minimum time. The spacecraft raced past Pluto at 31,000 miles per hour, gathering more data in a few hours than ground-based telescopes had collected in decades of observation. That flyby approach allowed New Horizons to be relatively small and lightweight, about the size and mass of a grand piano. A mission designed to orbit Pluto would have needed to carry enough fuel to slow down from interplanetary speeds, requiring a spacecraft perhaps 10 times more massive. The rocket equation makes orbital missions to distant targets extraordinarily challenging compared to flyby missions. This trade-off between mission complexity and scientific return appears throughout space exploration. The Juno mission currently orbiting Jupiter uses a highly elliptical orbit that takes it very close to the planet briefly, then far away for most of each orbit. This approach minimizes the spacecraft's exposure to Jupiter's intense radiation while still enabling detailed studies of the planet's interior, magnetic field, and atmospheric dynamics. Each close approach to Jupiter lasts only a few hours, but Juno's sophisticated instruments can gather tremendous amounts of data during these brief encounters. The spacecraft then spends weeks transmitting that data back to Earth during the quieter portions of its orbit. It's an elegant solution that maximizes scientific productivity while working within the constraints imposed by physics, engineering, and budget limitations. But what about truly revolutionary propulsion concepts that might break free from these limitations? Researchers are investigating several approaches that could potentially enable much higher speeds than current technology allows. Fusion ramjets, first proposed in the 1960s, would collect interstellar hydrogen as fuel and fuse it in flight, potentially achieving significant fractions of light speed. The Bussard ramjet concept is particularly intriguing because it wouldn't need to carry fuel for the entire journey. Instead, it would use magnetic fields to collect hydrogen from the interstellar medium and fuse it in an onboard reactor. Computer models suggest that such a system could potentially accelerate to 10 or 15% of light speed, fast enough to make interstellar missions feasible within human lifetimes. However, the engineering challenges are staggering. The magnetic scoop would need to be thousands of kilometers across to collect enough hydrogen, and we're nowhere close to building fusion reactors that could operate reliably in the harsh environment of space. Even more problematically, detailed analysis suggests that the drag from the magnetic field might actually slow the spacecraft down more than the fusion thrust would speed it up. Antimatter propulsion represents the theoretical upper limit of rocket performance. When matter and antimatter annihilate, they convert 100% of their mass into energy, the most efficient reaction possible in our universe. Antimatter rockets could theoretically achieve 40 to 50% of light speed, fast enough to reach nearby stars in just a few decades. The problem is that we can barely make antimatter, let alone store it safely for space missions. The entire annual production of antimatter at CERN weighs less than a nanogram, billionths of a gram. To power an interstellar mission would require kilograms of antimatter, representing millions of years of production at current rates. And storing antimatter requires perfect magnetic confinement systems that don't exist yet. Even if we solved the production and storage problems, antimatter rockets would face other challenges. The gamma rays produced by matter-antimatter annihilation would require massive radiation shielding to protect both the crew and the spacecraft's electronics. The thrust systems would need to handle reaction products moving at significant fractions of light speed. We're talking about engineering challenges that push the absolute limits of what's physically possible. But let's step back from these far future concepts and consider what might be achievable in the nearer term with advanced versions of current technology. Nuclear thermal rockets tested successfully in the 1960s and 70s could potentially be optimized to achieve exhaust velocities of 15 to 20 kilometers per second, 3 to 4 times better than chemical rockets. Such systems could enable Mars missions with transit times of 2 to 3 months, making human exploration of the red planet much more practical. The reduced travel time would minimize crew exposure to cosmic radiation, reduce the psychological stresses of long confinement, and allow for more frequent launch opportunities. NASA's current nuclear thermal propulsion development program aims to have flight-ready systems by the 2030s. Nuclear electric propulsion, which uses nuclear reactors to power ion engines, could achieve even higher performance for cargo missions. These systems could operate continuously for years, gradually accelerating payloads to speeds that chemical rockets simply can't match. Large cargo ships using nuclear electric propulsion could potentially reach Mars in 4 to 6 months, while carrying much more payload than chemical systems. The upcoming DARPA demonstration rocket for Agile Cislunar Operations, or DRACO, will test nuclear thermal propulsion in space for the first time since the 1970s. Scheduled for launch in 2026, DRACO will demonstrate that nuclear rockets can operate safely and efficiently in the space environment. Success could pave the way for much faster deep space missions using nuclear propulsion, but all of these advanced propulsion systems still face fundamental limitations imposed by physics. Even with perfect nuclear rockets, achieving high speeds requires enormous amounts of energy. To accelerate a single kilogram of mass to 10% of light speed requires about 4.5 times 10 to the 15th joules of energy, roughly equivalent to the electrical output of a large power plant operating for several days. This energy requirement scales linearly with mass, so accelerating a spacecraft massive enough to carry humans and life support systems requires truly staggering amounts of energy. Even if we could build perfect fusion rockets with 100% energy conversion efficiency, the fuel requirements for high-speed interstellar missions would be enormous. We might need spacecraft that are 99% fuel by mass, leaving almost no room for payload. The relationship between energy and speed becomes even more challenging at relativistic velocities, speeds that are significant fractions of light speed. As you approach light speed, your kinetic energy increases without limit, requiring infinite energy to reach light speed itself. This isn't just an engineering problem, it's a fundamental limit imposed by the structure of space-time. Einstein's special relativity shows us that mass and energy are equivalent, related by his famous equation E equals mc squared. As you accelerate an object, you're adding kinetic energy to it, which effectively increases its mass. The faster you go, the more massive you become, requiring ever more energy to accelerate further. This creates an insurmountable barrier at light speed that no amount of advanced technology can overcome. These relativistic effects become noticeable at surprisingly low speeds by cosmic standards. At 10% of light speed, your mass increases by about 0.5%. At 50% of light speed, your mass nearly doubles. At 90% of light speed, your mass becomes more than twice what it was at rest. Practical spacecraft would hit these relativistic limitations long before achieving the speeds needed for rapid interstellar travel. But perhaps the most sobering limitation isn't technical, it's temporal. Even with perfect propulsion systems that could accelerate spacecraft to significant fractions of light speed, the distances between stars are so vast that interstellar journeys would still take decades or centuries. The nearest star system, Alpha Centauri, is over 4 light-years away. Even traveling at 20% of light speed would require a journey of more than 20 years. This temporal challenge forces us to confront a profound question about the nature of exploration itself. Throughout human history, our greatest journeys have been measured in months or years, not decades or centuries. The Polynesian navigators who discovered remote Pacific islands undertook voyages lasting weeks. Magellan's circumnavigation of the globe took 3 years. Even the Apollo missions to the Moon required only days of travel time. Interstellar distances represent a qualitatively different challenge, one that pushes against the fundamental limits of human psychology and social organization. A journey to Alpha Centauri lasting 20 years would span nearly a quarter of a human lifetime. The crew members who departed Earth would be middle-aged by the time they arrived, assuming they survived the journey at all. Everyone they knew on Earth would have aged 2 decades, and the world they left behind would have changed in ways impossible to predict. This temporal disconnect creates what researchers call the generation ship problem. For truly distant destinations, we might need spacecraft designed to support multiple generations of travelers, with the descendants of the original crew completing journeys their grandparents began. Such missions would require not just advanced technology, but entirely new forms of social organization and psychological adaptation. The psychological challenges of long-duration space travel are already apparent in much shorter missions. Astronauts on the International Space Station, isolated for just 6 months to a year, report significant psychological stresses despite constant communication with Earth and the knowledge that rescue is possible. Imagine those stresses magnified by decades of travel through the void, with no possibility of return and no guarantee of finding anything worthwhile at the destination. Recent studies of isolated populations, Antarctic research stations, submarine crews, Mars simulation facilities reveal consistent patterns of psychological breakdown over extended periods. Social hierarchies collapse, interpersonal conflicts escalate, and individual mental health deteriorates. These problems appear to be fundamental aspects of human psychology, not engineering challenges that can be solved with better technology. But let's consider what we might achieve within our own solar system using the propulsion technologies we've discussed. Mars, our most likely target for human expansion, could become accessible with journey times measured in weeks rather than months, using advanced nuclear propulsion. The psychological and physiological stresses of a 6-week journey are manageable. Those of a 6-month journey are much more challenging. The asteroid belt, containing vast mineral resources that could support space-based civilization, lies within reach of nuclear electric propulsion systems. Spacecraft could travel between Earth and the asteroid belt in months rather than years, making regular cargo runs economically feasible. The low gravity and lack of atmosphere on most asteroids would make landing and takeoff relatively easy compared to planetary surfaces. Jupiter's moons present some of the most intriguing destinations in the solar system. Europa's subsurface ocean might harbor life that evolved independently from Earth. Ganymede, the largest moon in the solar system, has its own magnetic field and might contain more water than all of Earth's oceans. Io's volcanic activity provides a natural laboratory for studying planetary geology. All of these worlds could be reached in 1 to 2 years using advanced propulsion systems. Saturn's moon system offers equally fascinating targets. Titan, with its thick atmosphere and methane lakes, presents an environment so alien it might as well be another planet. Enceladus shoots geysers of water into space from its subsurface ocean, potentially carrying signs of life that could be detected by spacecraft flying through the plumes. These missions could revolutionize our understanding of life in the universe without requiring interstellar travel. The outer planets, Uranus and Neptune, remain largely unexplored since the Voyager flybys in the 1980s. Nuclear propulsion could enable orbital missions to these ice giants, revealing the structure and composition of worlds that represent a common type of planet throughout the galaxy. Understanding these planets could help us interpret observations of similar exoplanets around other stars. Even within our solar system, the speed limitations we've discussed create interesting trade-offs between mission duration and scientific return. Fast flyby missions can reach distant targets quickly but provide only brief observation opportunities. Orbital missions take longer to arrive but can study their targets for years or decades. The choice between speed and scientific capability depends on mission objectives and available resources. The upcoming Europa Clipper mission exemplifies this trade-off. Rather than attempting a direct, high-speed trajectory to Jupiter, the mission uses a complex gravity assist sequence that takes 5.5 years but arrives with enough fuel to perform dozens of close flybys of Europa. The extended travel time enables a much more capable scientific mission than a faster direct approach would allow. This principle applies throughout space exploration. The Cassini mission's 7-year journey to Saturn enabled 13 years of operations in the Saturn system, making discoveries that wouldn't have been possible with a faster but fuel-limited approach. Sometimes, patience yields far greater rewards than speed. But speed does matter for certain types of missions, particularly those involving human crews or time-sensitive scientific objectives. Solar observation missions need to reach their targets quickly to capture specific solar events. Asteroid deflection missions would require rapid response times to be effective. Human missions benefit from shorter travel times to reduce crew exposure to radiation and psychological stress. The key insight is that different missions require different approaches to the speed versus capability trade-off. There's no single best speed for space travel, only optimal speeds for specific mission requirements. This is why space agencies develop diverse portfolios of propulsion technologies rather than focusing on a single approach. Current research into advanced propulsion focuses on several promising directions. Breakthrough: Starshot's laser-propelled light sails could potentially reach 20% of light speed, but only for tiny payloads weighing grams rather than tons. Nuclear pulse propulsion could achieve several percent of light speed for larger payloads, but requires technology that doesn't exist yet and might never be politically acceptable. Fusion ramjets could theoretically reach 10 to 15% of light speed by collecting fuel from the interstellar medium, but the engineering challenges are staggering and might be fundamentally unsolvable. Antimatter rockets could reach 40 to 50% of light speed, but require antimatter production capabilities millions of times greater than current technology provides. Each of these concepts pushes against different fundamental limitations: energy requirements, materials, science, political acceptability, or basic physics. The history of technology suggests that some of these barriers will eventually be overcome, but others might prove insurmountable. Predicting which technologies will succeed requires understanding not just engineering challenges, but also economic, political, and social factors. The development timeline for advanced propulsion technologies is measured in decades, not years. Nuclear thermal rockets, first tested in the 1960s, are only now approaching practical deployment for space missions. Fusion power, promised for decades, remains perpetually 20 to 30 years away from commercial viability. Antimatter production and storage face challenges that might require centuries to solve, if they can be solved at all. This slow pace of development reflects the fundamental difficulty of the challenges involved. Space propulsion operates at the intersection of multiple scientific disciplines: physics, chemistry, materials, science, nuclear engineering, each with its own unsolved problems. Progress requires breakthroughs across all these fields simultaneously, making rapid advancement unlikely. But the potential rewards justify the long development timelines. Advanced propulsion technologies could transform human civilization by making the solar system accessible for exploration, resource extraction, and eventual settlement. The asteroid belt alone contains more platinum than has ever been mined on Earth. The outer moons harbor more water than all terrestrial oceans combined. The energy resources of the solar system dwarf anything available on Earth. The economic implications of faster space travel extend far beyond scientific exploration. Consider the current cost of delivering cargo to Mars, roughly $50,000 to $100,000 per kilogram, using chemical propulsion. Advanced nuclear propulsion could potentially reduce these costs by an order of magnitude, making Mars colonization economically feasible rather than just technically possible. This cost reduction comes from several factors. Nuclear propulsion systems can carry much larger payloads for the same fuel mass, reducing the number of launches required. Shorter travel times mean less wear and tear on spacecraft systems, improving reliability and reducing mission costs. Faster cargo delivery enables more responsive supply chains for space settlements, reducing the need for extensive local manufacturing capabilities. The SpaceX Starship represents an interesting case study in how engineering approaches can dramatically affect space travel economics. By focusing on reusability and mass production rather than exotic propulsion technologies, SpaceX aims to reduce launch costs by factors of 10 to 100. This approach suggests that sometimes evolutionary improvements in conventional technology can be more impactful than revolutionary breakthroughs in advanced concepts. But even with dramatically reduced costs, the fundamental physics of space travel impose limits on how fast we can practically move through the solar system. The energy requirements for high-speed travel scale with the square of velocity, meaning that doubling your speed requires 4 times as much energy. This quadratic relationship creates a natural economic barrier to extremely high-speed missions. Consider a hypothetical Mars mission using nuclear thermal propulsion. Reducing travel time from 6 months to 3 months might require twice as much fuel. Cutting it to 6 weeks could require 4 times as much fuel. At some point, the marginal benefit of faster travel doesn't justify the exponentially increasing costs. Mission planners must find the sweet spot that balances speed, cost, and mission requirements. This optimization problem becomes even more complex when you consider the infrastructure required to support high-speed space travel. Nuclear propulsion systems require uranium fuel, sophisticated reactors, and specialized handling facilities. Ion drives need xenon propellant and high-power electrical systems. Solar sails require precision manufacturing of ultra-thin reflective materials. Each propulsion technology demands its own industrial ecosystem. The development of these ecosystems takes time and represents enormous capital investments. The nuclear industry took decades to mature after the first controlled nuclear reaction in 1942. The semiconductor industry required similar timescales to evolve from the first transistor to modern microprocessors. Space propulsion technologies will likely follow similar development curves, with practical applications emerging decades after initial scientific breakthroughs. But there's reason for optimism about the pace of development. Modern computational tools allow engineers to simulate and optimize propulsion systems in ways that weren't possible during earlier eras of space technology development. Machine learning algorithms can identify optimal trajectories and system configurations that human designers might miss. Advanced materials science is producing substances with properties that seemed impossible just decades ago. The James Webb Space Telescope demonstrates how advanced engineering can overcome seemingly impossible challenges. Its segmented mirror deploys and aligns in space with precision measured in nanometers. Its sunshield, larger than a tennis court, unfolds through a sequence of hundreds of precisely choreographed steps. Its instruments operate at temperatures just a few degrees above absolute zero while maintaining perfect stability. These achievements suggest that equally impressive advances in propulsion technology might be possible. Recent breakthroughs in fusion research provide another reason for cautious optimism. The National Ignition Facility achieved fusion ignition in December 2022, producing more energy from fusion reactions than was directly input by the lasers. While this is still far from practical fusion power, it demonstrates that the fundamental physics of controlled fusion is achievable with current technology. Private companies like Commonwealth Fusion Systems and TAE Technologies are pursuing alternative approaches to fusion that might be more suitable for space applications than the massive tokamak reactors being developed for terrestrial power generation. Compact fusion reactors designed specifically for spacecraft could potentially enable much faster interplanetary travel within the next few decades. The development of artificial intelligence also offers new possibilities for space exploration. AI systems could potentially manage complex propulsion systems more effectively than human operators, optimizing performance in real time and adapting to changing conditions. Autonomous spacecraft could execute complex gravity assist maneuvers without human intervention, enabling missions to distant targets that would be impossible with current communication delays. Machine learning algorithms are already being used to optimize spacecraft trajectories and identify efficient paths through the solar system. The European Space Agency's Gaia mission uses AI to process the enormous datasets required for precision navigation and stellar mapping. Future missions could use similar techniques to optimize propulsion system performance and identify opportunities for faster travel. But perhaps the most important factor affecting future space travel speeds isn't technological, it's motivational. The Apollo program achieved remarkable speeds and precision because it had clear objectives, adequate funding, and strong political support. Similar commitment to advanced propulsion development could accelerate progress significantly compared to current funding levels. The total global investment in space propulsion research is probably less than the cost of a single major military aircraft program. NASA's budget for nuclear thermal propulsion development is measured in hundreds of millions of dollars per year, significant by academic standards, but tiny compared to other government expenditures. Increasing this investment by even modest amounts could dramatically accelerate development timelines. International cooperation could also accelerate progress. The International Space Station demonstrates that complex space projects can succeed through multinational collaboration. Similar cooperation on advanced propulsion development could pool resources and expertise from multiple countries, reducing costs and development times for everyone involved. China's rapid progress in space technology provides both competition and opportunity for international collaboration. Their successful Mars rover mission, lunar sample return, and space station construction demonstrate sophisticated engineering capabilities. Competition between space programs historically drives innovation, as seen during the Apollo era. Modern competition could similarly accelerate propulsion technology development. The commercial space industry adds another dynamic to propulsion development. Companies like SpaceX, Blue Origin, and others are investing private capital in advanced space technologies, potentially accelerating development compared to government-only programs. The profit motive creates incentives for rapid development and cost reduction that don't exist in purely scientific programs. But commercial development also faces limitations. Private companies focus on technologies with clear market applications and reasonable development timelines. Truly revolutionary propulsion concepts like fusion rockets or antimatter drives might require government investment because the development timelines and risks are too great for private capital markets. The intersection of government research, international cooperation, and commercial development creates a complex ecosystem for propulsion technology advancement. Success requires coordination between these different sectors, each with their own objectives and constraints. The most successful space technologies, like GPS, communication satellites, and Earth observation systems, have benefited from this kind of multi-sector collaboration. Looking ahead, the next 2 decades will likely see significant advances in nuclear thermal propulsion, ion drive efficiency, and solar sail technology. These improvements will enable faster missions throughout the solar system, reducing travel times to Mars from months to weeks and making the outer planets accessible for regular exploration. But truly, revolutionary advances, fusion rockets, antimatter drives, or breakthrough physics will likely require longer development timelines. The key insight is that space travel speed is not just a technical challenge, but a systems challenge involving physics, engineering, economics, politics, and human psychology. Progress requires advances across all these domains simultaneously. Understanding these interconnections helps explain why space travel development is slow and why dramatic breakthroughs are rare. The human element in space travel speed brings us to one of the most fascinating aspects of our cosmic journey. We are not just observers of the universe, but participants in its ongoing evolution. Every spacecraft we launch, every speed record we break, every new propulsion technology we develop represents the universe becoming aware of itself and reaching out to explore its own vastness. Think about this for a moment. The atoms in your body were forged in the nuclear furnaces of ancient stars that lived and died billions of years ago. The iron in your blood was created in a supernova explosion, so violent it briefly outshone an entire galaxy. You are quite literally made of stardust, and now that stardust has organized itself into a pattern complex enough to contemplate traveling back to the stars. This perspective transforms our discussion of space travel speeds from a purely technical challenge into something much more profound. We're not just trying to move faster through space, we're participating in the universe's attempt to understand itself. Every mission we launch carries with it 4 billion years of evolution, 13.8 billion years of cosmic development, and the accumulated knowledge of human civilization. The Voyager probes, now racing through interstellar space at 38,000 miles per hour, carry golden records with sounds and images from Earth. These spacecraft are moving so slowly by cosmic standards that they won't approach another star for tens of thousands of years. Yet they represent something remarkable. Matter that was once scattered throughout the cosmos has organized itself into machines capable of carrying messages between star systems. When we measure spacecraft speeds in miles per hour or kilometers per second, we're using human-scale units that make the numbers comprehensible, but from a cosmic perspective, even our fastest spacecraft are barely moving. The solar system itself is racing around the center of the Milky Way galaxy at about 515,000 miles per hour. Our entire galaxy is moving through space at over 1 million miles per hour relative to the cosmic microwave background radiation. This cosmic motion means that spacecraft speeds are always relative to something. The Parker Solar Probe's record-breaking speed of 430,000 miles per hour is measured relative to the Sun, but the Sun is moving relative to nearby stars, which are moving relative to the galactic center, which is moving relative to other galaxies. In the grand cosmic dance, everything is in motion, and speed becomes a matter of perspective. The cosmic microwave background radiation provides the closest thing we have to an absolute reference frame for motion. This radiation, the afterglow of the Big Bang, fills all of space and provides a backdrop against which we can measure our motion through the universe. Relative to this cosmic reference frame, Earth is moving at about 827,000 miles per hour as we orbit the Sun, travel around the galaxy, and participate in the expansion of the universe itself. These cosmic velocities dwarf anything we've achieved with spacecraft, yet they're invisible to us because we're carried along by the same motions. It's like being on a train. You don't feel the train's speed because you're moving with it. Similarly, we don't feel Earth's motion through space because we're part of the same gravitational system. This illustrates a fundamental principle. Motion is always relative, and speed only has meaning when measured against a reference frame. The expansion of the universe adds another layer of complexity to cosmic motion. Space itself is expanding, carrying galaxies away from each other at speeds that increase with distance. The most distant galaxies we can observe are receding from us at significant fractions of light speed, not because they're moving through space that fast, but because the space between us is expanding. This cosmic expansion represents motion on scales that make even our most ambitious spacecraft speed seem insignificant. But here's what's truly remarkable. Despite these vast cosmic motions, despite the enormous scales and incredible speeds involved in the universe's operation, we've managed to navigate through space with extraordinary precision. When the New Horizons spacecraft flew past Pluto after a 9-year journey, it arrived within minutes of its predicted time and came within a few thousand miles of its target after traveling over 3 billion miles. This precision is achieved through our understanding of orbital mechanics, the mathematical description of how objects move under the influence of gravity. These equations, first worked out by Johannes Kepler, and Isaac Newton centuries ago allow us to predict the positions of planets, asteroids, and spacecraft with incredible accuracy. We can calculate where Mars will be 6 months from now to within a few kilometers, despite the fact that it's traveling through space at 53,000 miles per hour. The mathematics of orbital mechanics reveals something beautiful about the universe. It operates according to comprehensible laws that we can discover and use. The same equations that describe a ball thrown on Earth also describe the motion of planets around stars and galaxies around each other. This universality of physical laws is what makes space exploration possible. We can predict and control the motion of spacecraft because the universe follows consistent, discoverable rules. But orbital mechanics also impose fundamental constraints on how fast we can travel through space. Every orbit has a specific energy associated with it, and changing from one orbit to another requires adding or removing energy. To escape Earth's gravity well and travel to other planets requires achieving escape velocity, about 25,000 miles per hour. To escape the solar system entirely requires even higher speeds, about 37,000 miles per hour relative to Earth. These escape velocities represent the minimum speeds required for interplanetary and interstellar travel. You can't get to Mars without first achieving Earth escape velocity, and you can't reach other star systems without achieving solar escape velocity. These aren't arbitrary engineering limitations, they're fundamental requirements imposed by the gravitational structure of the solar system. The energy requirements for achieving these speeds help explain why space travel is so challenging. Accelerating 1 kilogram of mass to Earth escape velocity requires about 312 million joules of energy, roughly equivalent to the energy content of 2.5 gallons of gasoline. But rockets are terribly inefficient at converting fuel energy into kinetic energy, so the actual fuel requirements are much higher. This inefficiency stems from the fundamental physics of rocket propulsion. Chemical rockets work by burning fuel and expelling the hot gases at high speed. But most of the energy goes into heating the exhaust gases rather than accelerating the spacecraft. Even the best chemical rockets convert only a small fraction of their fuel's chemical energy into useful kinetic energy for the spacecraft. More advanced propulsion systems like ion drives and nuclear rockets are much more efficient at converting energy into spacecraft motion. Ion drives can achieve specific impulses 10 times higher than chemical rockets, meaning they can produce the same velocity change with much less propellant mass. Nuclear thermal rockets could potentially achieve specific impulses 2 to 3 times higher than chemical systems, but even these advanced systems face fundamental thermodynamic limits. The maximum theoretical efficiency for any heat engine is given by the Carnot efficiency, which depends on the temperature difference between the hot and cold reservoirs. For space-based nuclear thermal rockets, this efficiency is limited by the melting point of reactor materials and the temperature of space, which acts as the cold reservoir. These thermodynamic constraints mean that even perfect nuclear rockets have limited performance compared to more exotic propulsion concepts. Fusion rockets could potentially achieve much higher performance because fusion reactions produce much higher temperatures than fission reactions. But fusion technology remains decades away from practical space applications, despite billions of dollars of investment and decades of research. The timeline for developing advanced propulsion technologies reflects the fundamental difficulty of the challenges involved. Nuclear thermal rockets were first tested successfully in the 1960s, but practical space applications are only now becoming feasible. Fusion power has been 20 years away for the past 50 years, and might remain so for decades more. Antimatter production and storage face challenges that might require centuries to solve. This slow pace of development is frustrating for those eager to explore the cosmos, but it reflects the reality of pushing against fundamental physical limits. Each advance in propulsion technology requires breakthroughs in multiple scientific disciplines simultaneously. physics, chemistry, materials, science, nuclear engineering, and others. Progress is necessarily slow because it requires coordinated advances across all these fields, but the potential rewards justify the long development timelines and enormous investments required. Advanced propulsion technologies could transform human civilization by making the solar system accessible for exploration, resource extraction, and eventual settlement. The energy and material resources of the solar system dwarf anything available on Earth by factors of millions or billions. The asteroid belt alone contains more platinum than has ever been mined on Earth, more rare Earth elements than exist in all terrestrial deposits, and enough iron to build structures larger than continents. The moons of the outer planets harbor more water than all of Earth's oceans combined. The Sun provides more energy in 1 second than human civilization has used throughout its entire history. These resources could support a space-based civilization orders of magnitude larger and more prosperous than anything possible on Earth alone. But accessing these resources requires the ability to travel quickly and efficiently throughout the solar system. Current chemical propulsion makes most asteroid mining economically unfeasible because the energy cost of reaching and returning from the asteroid belt exceeds the value of any materials that could be extracted. Advanced propulsion technologies could change this equation dramatically, making space-based resource extraction profitable and sustainable. The economic transformation enabled by faster space travel extends beyond resource extraction to manufacturing, research, and human settlement. Zero gravity and vacuum conditions enable manufacturing processes impossible on Earth: perfect crystals, ultra-pure materials, and massive structures that would collapse under their own weight in Earth's gravity. But these advantages are only accessible if we can transport people and materials to space quickly and affordably. The International Space Station provides a glimpse of what's possible with current technology. Research conducted in the station's microgravity environment has led to advances in protein crystallization, materials science, and fundamental physics. But the station's research capacity is severely limited by the high cost and long lead times for transporting experiments to and from orbit. Faster, cheaper transportation could enable much more extensive space-based research and manufacturing. Human settlement of the solar system represents perhaps the most profound long-term consequence of advanced space propulsion. Mars, with its 24-hour day cycle, seasonal variations, and accessible water resources, could potentially support large human populations. But establishing such settlements requires the ability to transport thousands of people and millions of tons of equipment across interplanetary distances. Current mission architectures for Mars settlement envision cargo ships that take 6 to 9 months to reach the red planet, carrying perhaps 100 tons of payload per mission. Establishing a self-sustaining colony of even a few thousand people would require hundreds of such missions over many decades. Advanced propulsion could reduce these timelines dramatically, making Mars settlement feasible within a single generation rather than multiple centuries. The psychological and social challenges of space settlement are as important as the technical ones. Humans evolved for life on Earth's surface, with its specific gravity, atmosphere, and day-night cycle. Adapting to alien environments requires not just life support technology, but fundamental changes in human behavior and social organization. The speed of transportation affects these challenges by determining how isolated space settlements are from Earth. A Mars colony reachable in 6 weeks rather than 6 months would maintain much stronger cultural and economic ties to Earth. Faster transportation enables more frequent personnel rotation, emergency medical evacuation, and cultural exchange. These connections could be crucial for maintaining the psychological health and social stability of space settlements during their vulnerable early years. But faster space travel also raises profound questions about human identity and the future of our species. If we can travel quickly throughout the solar system establishing settlements on dozens of worlds with different environmental conditions, how will human evolution proceed? Will the descendants of Mars colonists develop different physical characteristics adapted to lower gravity and higher radiation? Will the children of asteroid miners evolve enhanced spatial reasoning abilities for three-dimensional navigation? These evolutionary pressures would operate over timescales of thousands or millions of years, but they raise important questions about the long-term consequences of space settlement. Are we creating the conditions for human speciation, the development of distinct human subspecies adapted to different environments? Or will rapid transportation and communication maintain sufficient genetic and cultural exchange to preserve human unity? The answers to these questions depend partly on the speeds we can achieve for interplanetary travel. If journeys between worlds take months or years, settlements will develop in relative isolation, potentially leading to genetic and cultural divergence. If travel times can be reduced to weeks or days, the solar system could function as a unified civilization with rapid exchange of people, ideas, and genetic material. Current research in space medicine provides insights into how human physiology adapts to different gravitational environments. Astronauts on the International Space Station experience bone loss, muscle atrophy, and cardiovascular deconditioning within months of exposure to microgravity. But these changes appear to be largely reversible with proper exercise and medical countermeasures. The long-term effects of partial gravity environments like Mars or the Moon are still unknown. The psychological effects of space travel and settlement are equally important but less well understood. Isolation, confinement, and separation from Earth's natural environment create stresses that don't exist in terrestrial exploration. The overview effect experienced by astronauts, a cognitive shift toward greater environmental awareness and spiritual connection, suggests that space travel fundamentally changes human consciousness in ways we're only beginning to understand. These psychological changes could be amplified by faster space travel, which would make the transition from Earth to space environments more abrupt and dramatic. Current astronauts have months of preparation and gradual adaptation to space conditions. Rapid transportation might require new approaches to psychological preparation and adaptation support. The development of artificial intelligence adds another dimension to the future of space exploration and settlement. AI systems could potentially manage complex life support systems, navigate through hazardous environments, and even serve as companions for isolated space travelers. But AI also raises questions about the role of humans in space exploration. If machines can explore more efficiently and safely than humans, why send people at all? The answer might lie in the unique capabilities that biological intelligence brings to exploration and settlement. Humans excel at pattern recognition, creative problem-solving, and adaptation to unexpected situations. We also have intrinsic motivation for exploration and discovery that's difficult to replicate in artificial systems. The combination of human creativity and AI capability could enable space exploration and settlement that neither could achieve alone. But the timeline for developing advanced AI capabilities might be shorter than the timeline for developing advanced propulsion technologies. If artificial general intelligence emerges within the next few decades, it could dramatically change the landscape of space exploration before we develop the propulsion systems needed for rapid interplanetary travel. AI systems might design better propulsion technologies, optimize mission planning, or even develop entirely new approaches to space exploration that we haven't considered. The intersection of AI development and propulsion technology creates interesting possibilities for the future of space travel. AI-designed spacecraft could potentially achieve higher performance than human-designed systems by optimizing configurations that human engineers might not consider. Machine learning algorithms could identify efficient trajectories through complex gravitational fields that would be impossible to calculate manually. Autonomous spacecraft controlled by advanced AI could potentially operate for decades or centuries without human intervention, gradually accelerating to high speeds using solar sails or ion propulsion. These systems could serve as our ambassadors to the outer solar system and eventually to other star systems, carrying human knowledge and culture to destinations we might never reach ourselves. The concept of digital consciousness transfer, while still highly speculative, offers another potential solution to the challenges of high-speed space travel. If human consciousness can be uploaded to digital form, it could potentially travel at light speed as information rather than being constrained by the physical limitations of biological bodies. Digital explorers could reach other star systems in years rather than millennia, investigate alien worlds, and transmit their discoveries back to Earth. But digital consciousness transfer raises profound philosophical questions about identity, continuity of experience, and what it means to be human. If you upload your consciousness to a computer, is the resulting digital entity still you, or is it merely a copy while the original you dies? These aren't just abstract philosophical puzzles, they're practical questions that any civilization attempting digital space exploration would need to answer. The timeline for developing consciousness uploading technology is highly uncertain and might be much longer than the timeline for developing advanced physical propulsion systems. The human brain contains roughly 86 billion neurons with trillions of connections, creating a system of staggering complexity that we're only beginning to understand. Mapping and simulating this complexity might require computational capabilities far beyond anything currently available. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this one at the left side of the screen. Why light speed travel would destroy us before we even arrive. In this video, discover the terrifying physics that make light speed travel not just impossible, but deadly. See you there.